This is my friend Melanie. Melanie loves drinking tea, except not too hot to where her tongue is going to burn. She wants to drink tea at a reasonable temperature before running out the door for school. Assuming that she has to leave the house within 20 minutes after making the tea, and it takes her 5 minutes to drink it, how long will it take for the tea to cool to 53 degrees if the tea has cooled from 70 degrees to 61 degrees within the first 6 minutes in the kitchen, which is at 20 degrees? Does she have enough time to finish drinking it before leaving? So in order to solve this problem, we have to use Newton's law of cooling. But before I show you and explain the equation for Newton's law of cooling, let's take a look at the graph. As you can see, the graph is an exponential graph that is decreasing. And it's decreasing is because the rate, or represented by the variable k, is negative. If it's negative, that means it's decreasing, and we're talking about the rate of it cooling down. So it has to decrease. If k were to be positive, then we'd be talking about heating it up, and the graph would look like this. And these graphs just represent the general equation. So to go back to the equation, I'm going to explain where the variables from the problem fit into the variables of the equation here. So if we look at what each of these stand for, basically we are going to take the final temperature after the time, which is 6 minutes, is going to equal the surrounding temperature, which in this case was 20 degrees room temperature, plus the initial temperature, which was 70 degrees, minus the room temperature, which was 20 degrees, multiplied by Euler's mathematical constant E to the power of the rate, which is what we're supposed to find, multiplied by the time it took, which was 6 minutes. So in order to find out how long it's going to take for it to cool to a certain temperature, we're going to have to use the information given prior, which is the 6 minutes it took to cool, and figure out the rate that the tea is cooling at. So I'm going to rewrite the equation with the variables plugged in, which is 61 equals 20 plus parenthesis 70 minus 20 parenthesis Euler's E to the power of negative k, which is the rate that we're supposed to find, times 6 minutes. So from here, you're just gonna solve it. You're gonna subtract 20 from both sides, and you're gonna get 41 equals 50 e to the power of negative k times 6. Divide 50 on both sides, and because k is negative, you can switch the reciprocal of the other side of the equation so that it's just e to the power of k times 6. Then we're going to take the natural log of both sides so that we can get k alone, and essentially just remove that Euler's E. And taking that to your graphing calculator, or whatever calculator that you have, you should end up with 0.0330751565. But because this is terms of rate, we're just going to round it simply to 4 decimal places, which is 0.0331. So now that we know the rate at which the tea is cooling at within the 20 minutes, we can just plug in the desired temperature that we want to reach so that we know how long it's going to take. Therefore, we're going to be solving for the variable t. So the new equation is going to be 53 degrees equals 20 degrees plus 70 minus 20, again, times Euler's E to the power of negative 0.0331, which is the rate at which it is cooling, times t, which is the unknown time. Lastly, to solve for how long it's going to take, it's not much different than solving for the rate, which we did earlier. So you're just going to take 20 from both sides, subtract them, and you're going to get 33 equals 50 times Euler's E to the power of negative 0.0331 times the time. Then we're going to divide 50 from both sides, and because we don't like that negative exponent, we're just going to get the reciprocal of the other side, which is then going to leave us with 50 over 33 equals Euler's E to the power of 0.0331 times t. Then, in order to get rid of the e, we're going to take the natural log of both sides, and that's going to leave us with the natural log of 50 over 33 is equal to 0.0331 t. Then we're just going to divide the rate from both sides, and you should end up with 12.553, but we're just going to round it to the nearest tenth, and that's going to be about 12.6 minutes. Now that we've found the first answer to our question, which is 12.6 minutes, that's how long it took for the tea to cool from 61 degrees to 53 degrees, now we have to determine whether or not she has enough time to finish drinking the tea before she has to leave for school. As you can see to the little timeline graph that I made, after the 12.6 minutes, she only has about 1.4 minutes left before she has to leave, meaning since it takes her 5 minutes to drink it, there's going to be some overtime. So in all, the whole process took about 23.6 minutes, but Melanie has to leave within the 20 minutes that the tea was made. So that gives it a 3.6 minute overtime, and unfortunately, she does not have enough time to finish drinking her tea.